In this video, we're going to talk about the sum of dice distribution, sometimes called a pyramid distribution. As you can see here, this is the theoretical distribution of the sum of dice. But let's go over here first and talk about the way this works. You have a pair of dice, dice 1, dice 2, each one having 6 sides, and then you sum the dice. So 2 ones will give you a 2 and a 2 will give you a 4. Let's say one die 1 has 5 and the other die has 4, gives you 9, and so forth. Now these numbers go from 2 to 12, so it's bounded by 2 and 12, so you have the sum of dice goes from 2 to 12. And then the counts, theoretically, so there's only 1 2 and there's only 1 12. There are 2 3s, 3 4s, 4 5s, 5 6s, 6 7s, as you can see here, and then it goes down. As you can see, 7 is the one that comes out the most, and it has a probability of almost 17%, while the sum of 2 comes out to be about 3. Now it's very symmetrical. 2 and 12 have the same probability. The sum of 2 has approximately 3%. The sum of 12 also has 3%. As you can see, something like the sum of 6 has a 14% chance of you seeing it, while the sum of 8 also has 14%. Now, these counts can be represented, or the percentages. In this case, in this diagram here, they're the percentages. As you can see, here's 15, and then we said, what, 17% for 7, which is approximately at the point where it is on the height. Now, one thing to consider, and I think this is what this video is about, is that the mean is 7, theoretically, and the standard deviation is about 2.45 for the standard deviation. Sure, the min is 2 and the max is 12, but the standard deviation, you'll find out, because we're going to demonstrate in a Python code, we're going to demonstrate some trials. You'll see the standard deviation will be within this area of 2.45, maybe a little bit less, a little bit more. And the mean will also be consistent, very close to 7. So let's look at my program here. I'm going to start this program, and I'm going to tell it to do 300 trials, throw the dice 300 times, and every time you throw it, show us the results, which will go pretty fast. And you'll see a demonstration of this. Okay, here's the demonstration. Roll 10 and 20 and so forth. You can see the average is already at 7, at 7.12 with 40 or 50 rolls. The standard deviation of 2.40 is very close to 2.45. And it keeps going. Now, the thing with the sum of dice is that there are no outliers. It's bounded from 2 to 12. And because they're both fair dice, the dice are fair, there's no skewness here, except for some of those rare occasions where, randomly it comes out. Sure, randomly, if you throw out 300 rolls, you could technically get all 7s. How likely will that happen? Very unlikely. As you can see, we're already at 260 rolls, and this is becoming a bit symmetrical. So 300. So you can see that there are 3. So the computer, the software, the Python code, threw the dice theoretically, right? Imaginatively, 300 times. And it had an average of 7.07 0.08. That's the average. So theoretically, 7s are supposed to come out the most. And in this case, in this theoretical, or this actually empirical, well, I guess we can say empirical observation, out of 300 rolls, we got an average of 7.08. Now, 300 rolls, 1,000 rolls, it's very rare we're going to have a perfect symmetrical distribution empirically. Now, standard deviation of 2.43, that seems to be true throughout most of these trials, because because of the dice being fair, it's bounded between 2 and 12. It stays within that range of 2.4. Very rarely do you see it go to 1.96 or something, or even above, like 2.7. But because of the skewness or the randomness of this type of trials. Let's try again. Let's try another 300, and let's see what we got. So this Python code I developed about a couple of months ago, and I'm really liking it. It's turning out pretty good. It's going. It should pop up pretty soon. There it is. 6 rolls and so forth. After 14th roll, you already got a 2.47 and an average of 7.19. As we look at this more closely, you can see that a lot of action is happening between 5 and 9, right? And then a little more between 3 and 11, and 2 and 12 don't get too much action. But in this case, you can see that 12 is getting the sum of 12s are a little bit higher than the sum of 2s. The average is at 7.10, and the standard deviation is, look how the standard deviation doesn't fluctuate as much. We're at 2.49, which is pretty amazing. 2.45, I believe, is the or 2.44 something. 2.449, right, was the proper standard deviation. Now, this is interesting. At 300 rolls, you can see that 7 came out a lot more, and it's sort of symmetrical, but it isn't really, right? You can see that there's a lot less 2s than 12s. We can say that there are 15 throws for 2 and easily above 20 for 12s. So randomly you expect the distributions, another set of empirical values, right, to be that way. Now let's see if we can jump a little bit higher. Okay, let's do 1,000 trials, meaning the dice will be thrown 1,000 times, and then every 10th throw we'll see the update in the histogram. Let's see if that works. Okay, so every 10th throw. So right now it's 30 throws, 41 throws, 51 throws. So it's going to reach up to 1,000 throws. So as you can see, it's barely at 100 throws. Average is at 7. Standard deviation is 2.48. As you can see, the sum of 2s and the sum of 12s, they're sort of evening out. But a lot of the action really is between 6 and 8 or 5 to 9. The 2s and the 12s are left out because only 3% of the time the 2s and the 12s will come out as a sum. As we're now almost at 300 throws, this is very similar to what we've seen before. But this time we are continuing on to 1,000 throws, and we want to see if it gives you a better distribution in terms of being symmetrical. But as you can see, 6 and 8 are not very symmetrical, are they? 5 and 9 are, so is 4 and 10, 3 and 12, and 2 and 12. So we'll see as we keep rolling, do we get 6 and 8 to be more balanced? But if it isn't, does that mean that this is an invalid observation or empirical data? No. As we all know now, empirical data is empirical. It's not theoretical. Theoretical is what we expect the distribution to be at. But right now you can see that at 600 throws almost, the average is at 7 and the standard deviation is 2.49. The standard deviation theoretically for this should be 2.449. So very close, as the average should be at 7. Now we're getting closer to 700 throws, and the distribution here is getting to be more and more balanced. But 6 and 8 seems to be a little bit off. But again, being that these type of observations are random, there's going to be some variation in the way these distributions look. If we do this again at 1,000 throws, it's going to have a different look to it, because randomly, this is how this process works. And we're almost at 1,000 rolls, and you can see the average is now lower at 6.94, but the standard deviation hasn't seemed to change at all. Still at 2.48, and we're getting close to 1,000 now. And there it is, 1,000. Well, it's getting there. It'll probably get there eventually. But 991 rolls, average at 6.95, and a standard deviation of 2.48. Again, very, very close to the theoretical. How close? Close enough for us to verify that the theoretical model matches very nicely with our empirical data, which is this distribution here that Python created for us.